Imagine a shape so fundamental, so pervasive, that it weaves through the very fabric of our reality. A pattern that manifests in the swirling smoke of a simple ring blown from a smoker's lips. The magnetic fields confining plasma in futuristic fusion reactors and the vast spiraling arms of galaxies. This shape is the torus, and the dynamic patterns it creates are known as toroidal fields. At its most basic, a torus is a donut-shaped surface generated by revolving a circle around an axis outside the circle itself. But beyond its geometric definition, the torus embodies principles of balance, continuity, and self-sustainability. Its closed-loop structure allows for continuous flow without beginning or end. This makes it a perfect vessel for dynamic systems where energy or matter circulates seamlessly. Toroidal fields are the manifestations of this torus shape in dynamic processes. They are self-organizing structures where energy flows in through one end, circulates around the center, and exits out the other side in a spiraling fashion. This creates a feedback loop that maintains the field's stability and coherence. From the smallest scales within atomic structures to the largest cosmic formations, toroidal fields are nature's way of organizing energy efficiently and sustainably. We propose that toroidal fields offer a universal model for understanding how energy and matter behave in both natural and engineered systems. The toroidal pattern is not confined to a single discipline or scale. It appears in fluid dynamics, electromagnetism, plasma physics, biology, and even in the architecture of the cosmos. This recurring pattern suggests an underlying principle or blueprint that governs the interactions and structures within our universe. So today, I invite you on a journey to explore how toroidal structures serve as a universal model of dynamic interactions, energy exchange, and stability. We'll delve into the heart of vortex rings in fluid dynamics, the fiery cores of tokamak reactors in plasma physics, and the aerodynamic elegance of wingtip vortices. Through these examples, we'll uncover how the toroidal field not only connects disparate phenomena, but also offers profound insights into the underlying principles that govern our universe. This is more than scientific exploration. It's a story of patterns that repeat themselves as above, so below, revealing a cosmic symmetry that binds the microcosm and the macrocosm. By examining each type of toroidal system, we develop an understanding of toroid mechanics and uncover insights that can be applied through the principle of correspondence between systems. So let's embark on this voyage of discovery, starting with the mesmerizing dance of vortex rings. Picture blowing a perfect smoke ring, the swirling donut of air that drifts effortlessly through space. This simple act encapsulates a profound principle. The toroidal field conserves energy and maintains coherence by containing its dynamics within a closed loop system. In the case of a vortex ring, the air molecules circulate around the torus, preserving vorticity and sustaining the ring's structure over surprisingly long distances. Toroidal fields conserve energy and maintain coherence by containing their dynamics within a closed-loop system. Circulation corresponds to the fundamental way energy or force moves within a system, confined within a stable structure. What's truly remarkable about vortex rings is their ability to transfer momentum and energy efficiently. Unlike turbulent bursts of air that dissipate quickly, a vortex ring maintains its form, allowing it to travel further with minimal energy loss. This efficient energy transfer is a hallmark of toroidal structures, suggesting that they are nature's preferred method for moving energy smoothly and sustainably. Toroidal structures facilitate efficient transfer of momentum and energy, allowing them to travel long distances without significant loss. In any system, be it fluid, electromagnetic, or cosmic, a toroidal structure maximizes energy transfer while minimizing dissipation. The stability of a vortex ring isn't just a fluke, it's a direct result of its toroidal topology. The donut shape balances internal and external forces, creating a self-regulating system that resists dispersion. This inherent stability is a universal feature of toroidal fields, providing a blueprint for how structures can maintain integrity amidst chaos. The topology of a torus provides inherent stability, balancing forces internally so the structure remains coherent over time. Across all fields, toroidal systems are self-regulating and self-sustaining because of their geometry. Now, let's journey to the cutting edge of energy research, the tokamak reactor, a device that promises to unlock the power of fusion. At its core lies a toroidal magnetic field that effectively confines superheated plasma, preventing it from touching the reactor walls. This confinement is crucial. Without it, the plasma would cool and the fusion reaction would cease. The toroidal field effectively confines energy within a closed boundary. This principle applies universally, as toroidal fields trap and confine energy to prevent loss or dispersion, maintaining coherence in systems from plasma to particles. The tokamak doesn't rely solely on a toroidal field. It ingeniously combines toroidal and poloidal vertical fields to create a stabilizing helical structure. This helical field balances the pressure and magnetic forces within the plasma, preventing instabilities that could disrupt the fusion process. It's a dance of fields, choreographed to sustain the most complex of interactions. Combining toroidal and poloidal elements creates a stabilizing helical structure. In any system, magnetic, fluidic, or biological, combining different field orientations increases overall stability by balancing multiple forces. What's more, the movement of plasma within the tokamak generates its own currents, reinforcing the magnetic fields that confine it. This self-sustaining feedback loop is a testament to the toroidal field's ability to induce internal forces that maintain its structure, a principle that echoes across natural systems. Currents and forces induced within the toroidal structure reinforce the field itself. Toroidal systems at all scales generate internal currents or forces that sustain their own topology, creating self-sustaining feedback loops. Shifting our gaze to the skies, let's consider the graceful flight of an airplane. As it slices through the air, a pressure difference between the upper and lower surfaces of the wings causes air to spill over the tips, forming wingtip vortices, toroidal structures that are a byproduct of lift. And these vortices emerge naturally to balance the asymmetry in forces, a phenomenon observed wherever differential pressures exist. The formation of toroidal vortices arises from imbalances in forces or pressures, indicating that toroidal fields emerge naturally wherever differential forces act. This applies across all scales, with toroidal fields forming as a way to balance asymmetries in force or energy. However, these wingtip vortices aren't just mesmerizing. They have practical implications. They create induced drag, a form of energy dissipation that affects the aircraft's efficiency. This interaction underscores how toroidal fields manage energy storage and dissipation, regulating efficiency within their environment. Energy dissipation in toroidal vortices impacts the larger system, such as drag and aerodynamics. More generally, toroidal fields manage how energy is stored or dissipated, regulating efficiency within a given environment. The story doesn't end there. The toroidal vortices generated by one aircraft can persist in its wake, affecting others that follow. This phenomenon illustrates how toroidal structures influence neighboring systems, setting up interconnected, cascading effects through the transfer and dissipation of energy. Toroidal fields carry energy away and impact other systems, such as downstream turbulence. This suggests that toroidal structures influence neighboring systems by dissipating and transferring energy, often setting up interconnected, cascading effects. The next time you watch a smoke ring drift lazily through the air or marvel at the silent flight of a bird, remember that you're witnessing the toroidal field in action. This is a subtle reminder that the patterns above are reflected below, and that we are all part of this magnificent, interconnected cosmos. In the realm of electromagnetism, toroidal structures take on a fascinating role through the formation of antipole moments. Unlike conventional dipole moments that radiate energy outward, antipoles are non-radiating configurations. They arise when electrical currents flow in a toroidal pattern, effectively canceling out external electromagnetic fields. This creates a hidden or dark state where the energy is confined within the toroidal structure, invisible to an outside observer. Toroidal fields produce unique electromagnetic moments, antipoles, which may be invisible from outside the system. This indicates that toroidal fields possess hidden or latent properties, able to localize forces internally without radiating outward. The beauty of toroidal systems lies in their ability to contain energy without leakage. In antennas and metamaterials, engineers exploit this property to design devices that minimize unwanted radiation. By arranging currents in a toroidal loop, energy circulates internally, reducing electromagnetic interference and enhancing efficiency. Toroidal systems can contain energy without radiating, reflecting a principle of inward-focused energy circulation. This quality can be generalized to other fields where energy is internally conserved and kept within a closed loop. While toroidal dipoles may be stealthy, they are far from inert. Their unique geometry allows them to interact selectively with external electromagnetic fields. This selective responsiveness is harnessed in advanced sensors and cloaking devices, where the toroidal structure modulates how the system absorbs or reflects electromagnetic waves. Toroidal systems respond selectively to external forces, interacting in unique ways that depend on their internal geometry. This points to a broader principle that toroidal fields are inherently sensitive to external environments, modulating how they absorb or reflect influences. Now let's set our sights on the grandeur of the cosmos, around massive objects like black holes and neutron stars. Matter spirals inward, forming accretion disks. These disks often adopt a toroidal shape, a direct consequence of the conservation of angular momentum As particles move closer to the central mass, they speed up, much like a figure skater pulling in their arms to spin faster. The toroidal structure naturally accommodates this increase in rotational speed, maintaining stability. Conservation of angular momentum is a key feature of toroidal fields, seen both in small and large-scale systems. Toroidal fields inherently conserve rotational momentum, acting as stable reservoirs of angular energy across scales. But the toroidal story doesn't end with the shape of the accretion disk. Magnetic fields entwined within these disks can become twisted and amplified, leading to the formation of powerful jets that shoot out along the poles of the central object. These jets channel vast amounts of energy and matter across interstellar distances, guided by the toroidal magnetic fields that direct and focus the flow. The interaction of magnetic fields with toroidal flows channels energy in directed pathways like jets. This principle generalizes to systems where toroidal fields direct and channel forces along specific axes, controlling energy release. These cosmic toroids also play a crucial role in the transport of energy. The dynamics within the accretion disk regulate how energy is radiated away, influencing the emission of X-rays and other high-energy phenomena observable from Earth. The toroidal structure ensures that energy moves efficiently from the chaotic inner regions to the surrounding space, a testament to the torus's role as a mediator of energy flow. Toroidal fields manage the transport of energy efficiently, controlling radiation and emission in a structured way. This suggests that toroidal fields are mediators of energy flow and radiation, regulating how energy moves between the core and the boundary. Shifting from the cosmic scale to the quantum realm, toroidal structures emerge in the behavior of light itself. Optical vortices are beams of light that possess orbital angular momentum due to their helical wavefronts. These beams have a phase that twists around the beam axis, creating a donut-shaped intensity profile, a toroidal structure in light. This property allows light to carry angular momentum, which can be transferred to microscopic particles. Toroidal wavefronts carry angular momentum in structured, quantized ways. This can be generalized to any field where toroidal structures impart angular momentum, suggesting a model of quantized energy and force distribution within toroidal systems. At the very center of an optical vortex lies a phase singularity, a point of zero intensity where the light's phase is undefined. This singularity is a hallmark of the toroidal nature of the beam, representing a critical point of equilibrium. It's a striking example of how toroidal fields often feature central regions of minimal or maximal intensity, embodying balance within their structure. The central singularity of an optical vortex, zero intensity, reflects a broader principle that toroidal fields often have central points of minimal or maximal intensity, representing critical points of equilibrium. These optical vortices aren't just theoretical curiosities, they have practical applications. Scientists use them to trap and manipulate tiny particles in optical tweezers, exploiting the angular momentum to rotate objects at the microscopic scale. This interaction between toroidal light fields and matter opens doors to advancements in nanotechnology, quantum computing, and optical communications. Toroidal fields exert specific forces on matter, enabling manipulation at both micro and macro scales. This dynamic reflects the ability of toroidal fields to interact with and influence material objects through the transfer of angular momentum or energy. Nature, ever the master engineer, employs toroidal structures within our very bodies. The human heart, in its ceaseless labor, generates toroidal vortices during blood ejection. These swirling flows ensure that blood moves efficiently through the chambers and vessels, minimizing energy expenditure while maximizing circulation. It's a perfect example of how toroidal patterns optimize flow in biological systems. Toroidal fields optimize flow and minimize energy expenditure in biological systems, such as blood flow in the heart. This suggests that toroidal structures are nature's way of ensuring efficiency in systems that rely on continuous flow and circulation. The toroidal motion of blood also reduces shear stress on the vessel walls. By maintaining a smooth, laminar flow, the heart protects itself and the circulatory system from the damaging effects of turbulence. This principle highlights how toroidal patterns can minimize the impact of external forces, safeguarding the integrity of the system's boundaries. Toroidal flow patterns reduce stress on boundaries, which can be applied universally to systems where toroidal fields minimize the impact of external forces, protecting the boundaries or membranes of a system. Moreover, these toroidal flows contribute to the synchronization of the heart's rhythm. The harmonious movement of blood supports the timing of contractions and the efficient coordination of the cardiac cycle. This resonance exemplifies how toroidal structures in nature serve as harmonizing elements, aligning with larger cyclic processes in both living and non-living systems. Toroidal structures resonate with natural rhythms, promoting synchronization and efficiency. This implies that toroidal fields in nature are harmonizing elements, aligning with larger cyclic processes in both living and non-living systems. In the microscopic world of material science, toroidal fields manifest as specific arrangements of magnetic moments within certain materials. These toroidal magnetic domains represent localized regions where the magnetic moments align in closed loops. This unique ordering affects the material's overall magnetic properties and can influence how it interacts with external fields. Toroidal fields create localized order within larger systems, contributing to the macroscopic properties of materials. This suggests that toroidal fields in general create structured, localized regions of influence that affect broader system behaviors. One of the most exciting aspects of these toroidal domains is their ability to couple magnetic and electric properties, a phenomenon known as magnetoelectric coupling. This interplay allows for the control of magnetic states using electric fields and vice versa. Such coupling positions toroidal structures as interfaces or bridges between interacting forces within complex systems. Toroidal fields enable coupling between different forces, such as magnetic and electric fields. This generalizes to the idea that toroidal fields are interfaces or bridges between interacting forces within any complex system. The stability and distinctiveness of toroidal magnetic domains make them prime candidates for advanced information storage technologies. By encoding data within these stable, localized structures, we can achieve higher storage densities and faster retrieval times. The toroidal fields act as reliable reservoirs of information, retaining their properties over extended periods. The stability and distinctiveness of Toroidal fields make them ideal for information storage as they retain their form and properties over time. And this suggests that toroidal fields are stable reservoirs of information or energy, providing reliable, long-term storage. In the vast expanses of space, magnetic fields weave intricate patterns that can become knotted and twisted, forming complex toroidal structures. These knotted magnetic fields are not just cosmic curiosities. They are vital in storing colossal amounts of energy within their topology. The entanglement of field lines creates a tension that holds energy in a stable configuration, much like a coiled spring ready to release its stored potential. The complex topology of knotted toroidal fields stores energy that can be released later. This implies that toroidal fields act as repositories of latent energy, holding it in a stable configuration until triggered by external forces. When the delicate balance of these knotted fields is disrupted, perhaps by the movement of plasma or external perturbations, a dramatic process called magnetic reconnection occurs. The field lines break and reconnect in new configurations, unleashing the stored energy in explosive events such as solar flares and coronal mass ejections. These phenomena send bursts of radiation and charged particles across the solar system, impacting planetary environments. The rearrangement of toroidal magnetic fields releases stored energy dramatically. This suggests that toroidal fields can act as catalysts for rapid energy release, either through reconnection or restructuring. On a more controlled scale, understanding knotted magnetic fields is crucial for plasma confinement in fusion reactors. The stability provided by toroidal configurations helps contain the high energy plasma needed for fusion reactions, preventing it from damaging reactor walls and maintaining the conditions necessary for sustained energy production. Toroidal structures contain and stabilize plasma, a dynamic applicable to systems requiring stability within highly energetic or unstable environments. This points to the broader stabilizing role of toroidal fields across complex systems. In the subtle dance of light within nonlinear optical media, toroidal solitons emerge as stable, self-reinforcing wave packets. These solitons maintain their shape and energy over long distances and times, thanks to a perfect balance between dispersion and nonlinearity in the medium. The toroidal structure allows them to propagate without spreading out or losing intensity. Toroidal solitons maintain stability due to a balance between internal forces. This can be generalized to any system where toroidal structures balance forces to maintain their integrity over long periods. The toroidal shape of these solitons effectively localizes energy within a confined region. This localization is crucial in applications like high-precision material processing, where energy needs to be concentrated in a specific area without affecting the surrounding material. The toroidal soliton's ability to confine energy mirrors how toroidal fields in other systems prevent energy dissipation. Toroidal solitons localize energy within specific regions. Across systems, toroidal fields confine energy to specific areas, ensuring that energy does not dissipate over time or space. Perhaps even more fascinating is the way toroidal solitons interact with one another. Unlike ordinary waves that can interfere and diminish, toroidal solitons can pass through each other or interact without losing their coherence or structural integrity. This property makes them ideal for applications in optical communication and quantum information processing, where maintaining signal integrity is paramount. Toroidal solitons interact without losing coherence, indicating that toroidal fields allow for non-destructive interaction between multiple systems. This suggests that toroidal fields mediate interaction without diminishing their own stability. Returning to the realm of aerodynamics, toroidal vortices play a crucial role in improving the performance of aircraft and wind turbines. Vortex generators, which are small devices placed on the surfaces of wings or blades, create controlled toroidal vortices that energize the boundary layer, the thin layer of air close to the surface. This energized boundary layer delays flow separation, reducing drag and preventing stall at lower speeds. Toroidal vortices control flow separation, optimizing system efficiency. This dynamic extends to systems where toroidal fields manage boundary interactions, maintaining order and preventing loss of energy. By maintaining smoother airflow over the aerodynamic surfaces, toroidal vortices generated by these devices enhance lift and overall efficiency. This improvement translates into better fuel economy for aircraft and increased energy capture for wind turbines. It's a practical application of toroidal fields, optimizing system performance by regulating internal dynamics. Toroidal vortices enhance system efficiency by maintaining smoother flow. This suggests that toroidal fields optimize system performance by regulating internal dynamics. Moreover, the introduction of toroidal vortices contributes to the overall stability of the flow around the aircraft or turbine blade. By reducing turbulence and smoothing out irregularities, these vortices ensure more predictable and controllable aerodynamic behavior, which is essential for safety and performance. Toroidal vortices contribute to flow stability, indicating that toroidal fields stabilize dynamic systems, preventing turbulence and maintaining equilibrium. In the industrial world of chemical engineering, toroidal flow patterns are harnessed to improve the efficiency of reactors. By designing reactors that promote toroidal circulation, engineers achieve enhanced mixing of reactants. This thorough mixing ensures that chemical reactions proceed uniformly, increasing yield and reducing the formation of unwanted byproducts. Toroidal flow enhances mixing, leading to more uniform interactions. This dynamic generalizes to systems where toroidal fields promote interaction and integration, ensuring efficient exchange of matter or energy. The toroidal flow not only improves mixing, but also optimizes mass and heat transfer within the reactor. Efficient heat distribution is critical for controlling reaction rates and preventing hotspots that could lead to undesirable reactions or even hazards. The toroidal circulation ensures that heat and mass are evenly distributed throughout the system. Toroidal flow patterns optimize transfer rates, suggesting that toroidal fields are ideal for efficient mass and energy transfer across boundaries. Furthermore, reactors utilizing toroidal flow designs offer better scalability and control. The predictable and uniform flow patterns make it easier to scale up processes from laboratory to industrial scales without losing efficiency or control over reaction conditions. This scalability is vital for meeting production demands while maintaining quality and safety. Toroidal flow allows for better control over system dynamics, indicating that toroidal fields offer scalable solutions for controlling the environment or energy in complex systems. As we draw our exploration to a close, let's pause to reflect on the journey we've undertaken, a voyage through the intricate and often hidden patterns that weave together the fabric of our universe. We've delved into the swirling elegance of smoke rings, the fiery cores of stars, the whispering currents of our own hearts, and the grand tapestries of galaxies. In each of these realms, the toroidal field emerges not just as a shape, but as a fundamental principle, a universal symphony playing the same melody across the scales of existence. Our journey began with the simplest manifestations of the toroidal field, the mesmerizing dance of vortex rings in fluid dynamics. Here we saw how energy and matter can circulate within a closed loop, conserving momentum and maintaining coherence. This basic principle of energy containment and conservation sets the stage for more complex behaviors. It's as if the torus whispers a secret that by embracing a circular path, systems can achieve balance and sustainability. Moving forward, we encountered the toroidal magnetic fields in tokamak reactors, humanity's ambitious attempt to harness the power of the stars. In these reactors, the toroidal field provides dynamic stability through geometry, confining plasma at temperatures hotter than the sun's core. It's a testament to how the toroidal structure can manage extremes, balancing internal and external forces to maintain equilibrium. Our ascent continued as we explored the efficient energy transfer and interaction facilitated by toroidal fields, from the wingtip vortices affecting aircraft efficiency to the hidden anapole moments in electromagnetism. We observed how toroidal structures optimize the movement and interaction of energy. They act as guardians, ensuring that energy flows smoothly where needed and remains contained when necessary. As we ventured into astrophysics and photonics, the toroidal field revealed its capacity for force balancing and optimization. In the swirling accretion disks around black holes and the helical wave fronts of optical vortices, toroidal structures manage asymmetries and direct forces along specific pathways. They become the conductors of a cosmic orchestra, harmonizing discordant energies into a coherent performance. In the realm of space physics, the toroidal field demonstrated its prowess in stability within energetic and unstable environments. Knotted magnetic fields store and release vast amounts of energy, shaping the behavior of stars and influencing entire galaxies. Here, the toroidal field is not just a mediator, but a catalyst, capable of initiating dramatic transformations while maintaining an underlying order. Our exploration of toroidal solitons in nonlinear optics and toroidal flows in chemical reactors showcased the torus's role in mediating complex interactions. These structures enable non-destructive interactions and efficient mixing, essential for advancing technologies in communication, energy, and manufacturing. The toroidal field emerges as a bridge between forces, facilitating interactions that might otherwise be impossible. Perhaps most profoundly, we saw how toroidal structures resonate with the rhythms of life itself. In the human heart, toroidal blood flow patterns reduce stress and synchronize with the cardiac cycle, promoting health and efficiency. This resonance extends to the synchronization of dynamics in optical solitons and the stability of plasma in fusion reactors. The toroidal field becomes a symbol of harmonizing complexity, aligning systems with the natural cycles that govern them. At the pinnacle of our ascent, we recognize the toroidal field as a scalable and universal archetype. It transcends specific contexts or scales, applying the same fundamental principles from the microscopic realms of quantum particles to the macroscopic structures of the cosmos. The toroidal field is the universe's way of echoing a simple truth that the patterns governing the spin of an electron are akin to those orchestrating the rotation of galaxies. So, what does this all mean? It means that by understanding the toroidal field, we're tapping into a universal language, a code written into the very essence of reality. This code tells us that balance and stability are achieved through geometry. The toroidal shape inherently balances forces, creating systems that are both stable and dynamic. Energy is best managed in closed loops. Containing energy within a toroidal structure optimizes efficiency and minimizes loss, a principle applicable in technology, nature, and even societal systems. Complex interactions require elegant solutions. The toroidal field facilitates interactions between disparate forces and phenomena, offering pathways to innovation and deeper understanding. Unity exists within diversity. Despite the vast differences in scale and context, the toroidal field serves as a common thread, uniting various disciplines under a shared framework. As we stand at the intersection of science, philosophy, and wonder, the toroidal field beckons us to look beyond the surface, to see the interconnectedness of all things. It challenges us to find the torus in the patterns of weather systems, in the structures of our brains, and perhaps even in the flow of ideas within societies. This understanding isn't just an academic exercise. It's a call to action. By embracing the toroidal model, we can innovate across disciplines, applying these universal principles to solve complex problems in energy, medicine, environmental science, and technology. We can foster interdisciplinary collaboration, breaking down silos between fields, recognizing that insights from one area can illuminate challenges in another, and we can cultivate a holistic perspective. Appreciate the interconnectedness of systems, leading to more sustainable and harmonious approaches in both science and daily life. In the end, the toroidal field teaches us that complexity arises from simplicity, and that the universe in all its vastness operates on fundamental principles that are accessible and understandable. It's a reminder that we are part of a grand design, participants in a cosmic dance choreographed by patterns that repeat from the smallest particles to the largest galaxies. So as you go forth, I invite you to look for the torus in the world around you. See it in the whirlpool of water down a drain, the formation of hurricanes, or the structure of DNA. Let it inspire you to ask new questions, seek deeper connections, and embrace the beauty of the patterns that bind us all. In the toroidal field, we find a mirror, a reflection of the universe's inherent elegance and our place within it. Thank you for joining me on this journey. May the insights of the toroidal field continue to inspire and guide you in all your explorations.